Austin Consultants are one of our alliance partners. These are the kind of approved partners that NI works with. Austin Consultants are kind of specialists in automation, real-time test, HAL, it's kind of real-time test, and HAL is probably what comes into this topic really. And you know, we've got a long history of working together. They're one of our most trusted advisors. So and I think Dave's got almost renowned as one of the top test cell real-time test developers in the country.
Thank you. Thank you.
I think I can go out on them and say that. And I think you've made a wise choice in coming to listen to him today. So I won't kind of gabble on too long, but I'll let Dave kind of well done for coming to this session.
Thank you. So thanks for coming. So as you just heard, this talk's really about test cells and kind of wider subject area than just test cells, because as you'll see hopefully over the next few slides, there's an increase in complexity of test cells, and they're becoming more hardware-in-the-loop embedded test systems as a whole. So hopefully I can guide you through some of these slides and give you a bit of an insight into our experience and how some of the frameworks, some of the NI frameworks, have helped us to help deliver systems for customers. So who am I? You've just heard Austin Consultants. I kind of head up the software for my sins with Austin Consultants, architect, and just recently, about a year ago, got the embedded developer qualification, one of the new NI qualifications. And who are we? You've heard all about us from just a few seconds ago. So I'm not going to read through this abstract, but this is kind of what I've just said. This is what I hope to get from the talk, and hope to give to you guys a bit of information about what we've done and how we've developed and how we've able to save clients time and money using test systems. So this is kind of what I want. It's a bit of an agenda of what I want to go through. I'm not quite sure how well we'll get on with time, but I want to get through the slides and get into actually running some kit, just kind of proving to you guys how easy it is to use and how you can get going really quickly with some of the frameworks and the tools. So first of all, I want to just ask the audience what's their perception? What to you guys is it defines a test cell? Is anybody willing to just put their hand up and test cell? Okay. So environmental testing. Oh, not environmental testing. Kind of more testing in a physical lab. Absolutely. This is a definition that I've picked up from somewhere on the internet. It's combining industrial machinery, precision control, and laboratory quality measurements. So this is kind of one definition. I mean, it can be defined in many different ways, but I think what you'll see as we kind of push through the slides is that test cells themselves are related in a very close sense with this other kind of key phrase that's become more prevalent in the last few years, hardware-in-the-loop test system. So would anybody like to kind of give a same kind of definition of hardware-in-the-loop test system? What would that how would that differentiate from a test system? Anybody?
It's a testing environment where your target hardware is surrounded by simulation and control and monitoring.
Absolutely.
Systems.
Absolutely, yeah. That's pretty much what it says here. Realistically simulate missing components of the control system. Absolutely. So here's an example. You've got your device under test. You've got a control system, or control model, or that's providing loading and actuators to your system. You're measuring the system via sensors, conditioning back into your test system. So that's I guess a traditional test cell. If you look at hardware-in-the-loop test system, it's very similar, and maybe a more complex system. A test cell would have multiple electronic units distributed together, but linked in the same way. So I borrowed this slide from NI. It kind of gives you an idea that this HIL embedded software validation is merging as test systems that require testing are getting more complicated. the embedded software validation that you get from model-based testing, and what you need to do in test cells is, excuse me, is merging into a kind of murky area with very, very similar requirements. This slide hopefully kind of demonstrates that subtle difference between a test cell and HIL. You can see here it can be kind of defined in the amount of simulated versus actual components in a system. Down the HIL area at the bottom there, you've got more simulated and less actual, but in test cell. Basically what I'm trying to get at is that the test cells and hardware in the loop testing is effectively, as things become more complicated, one and the same thing. Here's some examples of what you would call classic test cells. They've been, again, using model-based testing, model-based design to simulate parts of the environment that you can't, that make it easier to test your system, in a static place. Dynos, powertrains, components TestStand, wind tunnels, all sorts of places where embedded test and test cells happen. So this slide kind of is there to prompt what test cells can kind of give you throughout the whole software design cycle. If you can get yourself an embedded test system that is with you right through the design stages, through prototyping, through to deployment, validation and testing, you're reusing software, you're reusing code, reusing test cases, and it provides a much more testable and traceable design. And you can see here, VeriStand, it's a bit hard to see from this slide, but VeriStand can be used in all of these separate different areas. So more about VeriStand shortly, but VeriStand is how we've chosen to attack these kind of projects to provide us with a framework. So just to go back to basics a little bit, why would you want to do real-time test? Why don't you just test in TestStand, for example? So here's a common myth. With customers may come up with the statement that they automate testing already. Why on earth would they need a different framework to test their systems? But as you can see here, TestStand is based on ActiveX, so it's great as a PC test sequencer. But when you're talking about a little bit lower level, actually running the model, closing the loop on some of your design, then it's not the right tool. As I said here, it's great for static analysis, but not ideal for control, for dynamic validation and testing. Another common myth that we come across in our development is we don't need to test in real time. In fact, we already test faster. So this is just a common myth about what real-time testing. It doesn't mean fast. It means at a particular time. It means deterministic. We want something to happen at a certain number of seconds or a certain number of milliseconds after another event has happened. Or in terms of control, you want to close the loop as quickly as possible. A number of systems that we've run, you can run in real time. Also, interestingly, you can ramp up the rate that your models are running at. We'll talk more about models in a minute. If you ramp that time up, you can kind of run in simulated fast real time. Maybe run through your tests a little bit faster, but still deterministically if you've got slower systems. So when we come to a customer and we kind of hear requirements like these kind of requirements, they kind of prick up our ears and say, okay, maybe this is somewhere where we could use a embedded test framework. You can see the kind of things that people require. I mean, often design teams will be using tools such as MATLAB Simulink to define their models already in a design department. Quite often you want a tool that can utilize and pick up that expertise without having to translate it, without all the problems that translating from one person to another involves. So these are the kind of requirements that we hear from customers, and it kind of prompts us to think about real-time test. So I want to talk to you briefly about 4 example projects from our experience. What I'll kind of do is I'll kind of go through them and kind of pick out some of the challenges, if you like, requirements, another word for what, that have come out of these particular systems. And I'll cycle back to these later on at the end of the talk and tell you kind of how we were able to address these challenges. So test flow cell. What's a test flow cell? So this was a company from the oil and gas industry that wanted to test a new undersea pump. A flow cell, basically a big tank of water flowing around a pipe, or a liquid, may not have been water, and it's flow sensors, temperatures, lots of I/O. In fact, I think it was over 500 separate, distinct I/O channels. So that's quite a big challenge, to start with. But they also wanted closed-loop control. They wanted to control their pump. Interestingly, in this one, and again, one of these things that pricked up our ears, the designers of the pump were producing models for their PID, for their control models in Simulink. They wanted to prototype new control modes. They also wanted alarming. They wanted basic test sequencing. So this was our first foray into VeriStand. We didn't know about VeriStand when this customer came to us. We did a lot of research. We tend to do for a lot of projects, a lot of research as to what was the best solution. Of course, we could have come up with a custom solution. Perhaps we would have ended up charging the customer more money, but that's not what we do. We're consultants. We want to find the best solution for that customer. So in the research for these kind of requirements, we kept coming back to VeriStand. VeriStand, it allows you to build in Simulink models. It has alarming off the bat, has basic test sequence. So a lot of these key challenges were already met. So let's dive into another one. So here are another bunch of requirements. This is a high-speed dynamometer. So basically a big motor, which is this is a brake dynamometer, so simulating braking on a car. So these guys are running a really high speed. The control loops in their models are running in the region of 10 kilohertz. I mean, that's not really high speed. We're talking about acquisition and stuff, but in terms of control loops and control loop rates, 10 kilohertz is pretty fast. They've got a number of custom bespoke sensors. They required high time resolution inputs, frequency signals, PWM signals, and to get the resolution at 10 kilohertz is quite a challenge. Fast closed loop control. Again, they wanted it alarming. Again, their models were in the MATLAB environment. And again, they wanted. So you can already see, hopefully from the first two, that there's a number of things that are popping out that happen in all of these types of projects. So this is a slightly different project. The customer wanted to test a piece of kit that had multiple configurations. They wanted to basically take from a database a number of different models of the system and create an environment with certain, a number of these and a number of these things that were happening, and put in all sorts of I/O and different Modbus interfaces, RS-232 interfaces, a lot of different challenges. But at the core of what they wanted to do was an embedded test that was deterministic down to a millisecond or more level, but again with alarming, with channel monitoring. They also wanted to be able to, what was important on this one is they wanted to be able to script a scenario and run the test automatically. So there's a number of things that the test system should do, but it also needs to be scriptable, if you like. So the final one, just to give us kind of an idea of the different kind of techniques that are, or the different challenges that we faced. Again, similar things: high-speed control, low latency sensor, but multiple bus technologies. So this is where some of the NI kit can really help. So if we've got a system that integrates well with the NI kit, we can address things like CAN open, EtherCAT directly by having a system running on the PXI. They're already there. And most of these are already supported by something like the VeriStand framework. So I've kind of already mentioned it, but how do you, what can you do to, we've got all of these kind of requirements. What is there out there that does all of this kind of stuff? I mean, this is a bit of a cheat slide because it's actually and I sound like an NI sales rep, so that's the VeriStand kind of broad sheet. That's what VeriStand does. So all of these kind of things fall under the umbrella, which is one of the reasons why we have chosen to use VeriStand as that base software framework for these kind of applications. It allows us, we could write something yourself, but it allows us to just take that little step up immediately, give the customer something working relatively quickly, and not deal with all the kind of pipe work of pushing data around between systems. That's all kind of done for us, and then we can concentrate on the customer's requirements, their bespoke requirements, if you like, for their particular test cell. So I apologise if you guys have been to a talk already about VeriStand, but I'm just going to run over the basics of what is VeriStand, just so we can kind of understand it. Importantly for me, I come from a software background, so this tool is not only useful, but it has a good API, so you can programmatically interact with the program. If you wanted to, you could create your own user interface which has no branding on it at all. That's what some customers require, that's what other customers. So it's actually a .NET API. I know it's kind of maybe a banned word in our days, but it's a .NET API built by National Instruments, but that means it's interoperable with a lot of different languages, and hopefully we'll be able to show you some examples of interoperability with other languages at the end of the talk. Interoperability again with other languages, so models, which are a main part of VeriStand, which I'll show you in a second, where they sit in the system. We can support models from all sorts of different packages, languages. The models effectively are just DLLs. So any language that can compile a DLL or a .so file on Linux can be used as the model. There is stimulus generation built in. So once you have your simulation of your system running, what do you do with it? Okay, you get it running, but you want to interact with your system. You want to give it an impulse and see how it reacts, or give it a profile that you want to run. One of our customers at the moment wants to run a time-based model, which is effectively, it's an engine system, and it's effectively driving around a particular area. So it's a time-based throttle input model. So anything can be a model or a stimulus into your system. APIs again, it can be automated via TestStand and insert any other sequence, test sequencer. And as I said at the bottom here, we chose to build on top of VeriStand for a number of these projects rather than kind of reinvent the wheel. Key components of VeriStand. We'll bring it up in a second. You can kind of see the components, but effectively this area at the top here is driven by the .NET API. So this is done on the PC. So you have a real-time system in your, like a PXI system under the desk here, which is running a VeriStand engine. So this is where all of the real-time testing occurs. This stuff at the top here is the configuration of your system. So I guess you could call VeriStand a configuration-based real-time test system. So we've got system configuration telling what inputs, what outputs, and what inputs are mapped to what inputs of the model. So it's basically piecing together the components. And as long as you have all of these components together to start with, you don't have to be a programmer. Any one of your design team or even your operators can put these pieces together. In the middle there we've got stimulus generation. So this is an add-on. I mean, it's all part of VeriStand, but it allows you to push stimulus into the real-time test system. So they're set up so that you can push in a ramp on a signal or push in a square wave. And then this workspace is kind of unusual for LabVIEW, I guess. This user interface it's a dynamic user interface that you can add graphs and add indicators to whilst you're up and running. So dynamically, when the system's running, you don't want to stop your simulation, just add an extra graph, bring it up. We can show you that in a second. And then down on the real-time model, that's where all the brain happens. And what's quite interesting is that this is all written in LabVIEW, this engine. I don't think you can dig too deeply into it, but what it means is that this will this will run on any of the targets. So this will run, a lot of the PXI systems and the controllers are now moving over to the RT Linux. But this is all LabVIEW, so this is all just running on the real-time engine. So it's not come out very well on the slide here, but so this is a System Explorer. This is where you set up your system. We'll save that for when you've got the real thing up on the screen. Here's a dynamic workspace. You may have seen one of these. Just graphs, numeric controls. Looks a bit LabVIEW-y, but this can be reconfigured dynamically. And then you've got something that looks a little bit like TestStand, but I would say they're very different beasts. A lot of people say, "Oh yeah, VeriStand is just real-time. It's TestStand on real-time." It's not. I think they're quite different beasts. VeriStand is a software framework for real-time testing. But this stimulus profile editor allows you to do things like looping, stimulus generation. Okay, so onto the core part of VeriStand is the model. These can be from any kind of environment, and there's a list here of the kind of environments that. I mean, you can kind of forget all of that. It's anything that compiles to a DLL. So all of these things, what they do is compile to a DLL, and you can bring them into VeriStand. And the nice thing about being NI kit and being based in a PXI chassis is that any of the complex simulations that you need to do, any of the complex sensor decoding, custom protocols, that kind of stuff can be done on an FPGA, and the results of that can be pushed into the model. Quite a number of times we've used sensor simulation, so this is kind of you know that you want your sensor output to produce 5 volts, but it needs to be a certain waveform. Then we can do that on the FPGA and just interact with the FPGA very easily through VeriStand. You can obviously, of course, put high-speed control onto the FPGA. And the way that comes into VeriStand is literally a bunch of channels that's come through the FIFO. You don't even have to set up a FIFO through the FPGA. So it's a nice way of interacting with FPGA in real-time test. So custom devices, this is basically, there's a number of things that VeriStand supports off the shelf, but this is where we as an alliance partner come in. A lot of different, customers will have a lot of different extras to their system that are kind of custom to their particular application. Custom devices are just a plug-in system, if you like, for VeriStand, so that you can just add in your own protocol, this is talking to a Lambda DC power supply. We've produced custom devices for customers talking over Modbus. Different features that are just not supported. There's a nice interface to adding in extras to the system. But there's also a vibrant community of custom devices. I think these are all NI on this side. The bolding indicates that it's kind of NI system. So they're not. I don't know what the right word is. They don't come as part of VeriStand, but they're on the community and they're NI systems engineers. They've produced these, so they won't guarantee 100% that they work, but you can take the code and you can look at it and you can modify it if you need to. But all of these things over here, branching out into the aerospace industry, MIL 1553, all of these kind of extras that you can add on to the system. So I think in order to understand a little bit more about where VeriStand can help us as integrators, let's take a little bit of a peek under the hood of VeriStand. So VeriStand is running a primary control loop rate, at a certain 500 hertz, a kilohertz, 5 kilohertz, 10 kilohertz. All of these things happen every single cycle. A deterministic system. Basically this, you don't want to read all of that stuff. It can be boiled down to get inputs, map. Stimulus if you want to, and map again. And map, I mean putting the inputs to the outputs. Channel to channel mapping. Run your models. So it's basically inputs, models, outputs. That's all. So obviously the thing that NI kit does pretty well, let's bring the hardware, the physical world into the system. inputs and outputs. As you'd expect, it's an NI framework, so the NI hardware integrates very easily. But you can, as I said, with the custom devices, many other hardware can be supported very, very easily. So, enough of me waffling on. Let's let me show you how easy it is to integrate. Okay. Oh, I have to turn around to this. So, okay, it's the wrong side of my screen. So this is VeriStand. Let's just start afresh. So this is a system configuration. I've got a PXI system neatly under the desk here. It's just it's a 1042Q. It's a little quiet chassis. You wouldn't even know it's on. So the first thing you do with VeriStand is this one here is the system definition. So this is our configuration on the PC side. So this is running on my laptop. So this configuration is really just an XML file. It's defining what hardware is linked to what. So you can see here, here's my hardware, here's a controller, hardware. If I click on the controller, see if I tell you what, I'm going to find not. I know that it's file app, and I know that it's on a weird. IP address. So this is oops, sorry. This is where you set up the kind of the core primary controller. You might hear me talk about PCL, primary control rate. So this is going to run at 100 Hertz just for this demonstration. You know, you can tweak this here. There's lots of other settings as to whether to, stream channels. You don't need to worry about any of that. Let's look at our PXI chassis. You can see here, got a chassis. So we can use the hardware discovery wizard here to go and interrogate our system. Hopefully it will talk to it. Oh, okay, brilliant. So it's found that we've got a DAC card in the system. Twice as found. So it's now going to add it to the framework. And now you'll see we have a PXI DAC card in slot 3. So I just wanted to showcase how simple it is to, sorry, next one. In our configuration. So all I need to do is to add channels. If I want to use this, I can add a channel. I can decide whether it's an analog input, analog output. It even supports some of the more advanced things. I mean, you'll see this is very much like a Max interface, but it's giving you, say for a counter input, I can turn my counter input into an encoder input. No, if I click the right one, with 4 times encoding. And it's as simple as adding 2 counters. That's all the number of counters that are supported on that card. So you can see how quickly I've got counter. I can add, let's just quickly add a couple of analog outputs. Analog outputs. So to run this demo here, that's actually all I need, apart from the model. This is all the hardware I/O that I need. So that's, just come back to the slides for a second. So that's acquisition and generation. It's simple as that. Models themselves. So models are the important part of VeriStand. They're central. They're what getting the data in and out of the system is all about. They can be made in LabVIEW. Very simple to do that. We can showcase that in a second. But as I've said, you can use other tools to create your models. I've got, as an example, we've got, sorry, MATLAB running here, and this 2-degree of freedom helicopter that you see in front of us here, it's an educational demonstration tool. It's got a fairly complex control system because, as you can imagine, this has got a pitch rotor at the front here, and it's got, as soon as you increase the pitch, you have a gyro effect which starts spinning. So you've got a tail rotor, just as in a real helicopter, which will compensate for it. So this is a fairly complex model which uses feed forward, a linear quadratic resolver, and integral. Don't ask me about the maths inside there. But basically, we can just click up here, code, CLL code, C, build. VeriStand comes with a little header file which allows it to create the correct inputs and outputs and create a model. So I'm not going to go through that process now because it takes a few seconds. But if I open up this one, you'll see that inside the system definition here, because we've had customers playing with this as well today, you'll see a bunch of other models as well with rate limiters and joystick input in here. But this model here is literally, so if you look on here, this is a DLL from this area created from Simulink, and you can see here the Simulink imports and outputs, desired position, encoder inputs, and then voltage outputs are in the model. So literally, we've got our inputs in the hardware section, we've got our model in the middle here, and then we just use this tool here which maps our outputs, our inputs to our model, and our model outputs to our outputs. So once they're all mapped, this model deploys that configuration down to the PXI. And while that's happening, we then open up the user interface, which is again running on the PC. So this is kind of looking into the normal size screen. Just set up a few parameters correctly. And to make it not too noisy, I'm just going to give us a little bit of bias on here. And hopefully, I mean, you should never do live demos without checking them first, but power. So now this is an inherently unstable system. If it's actually under control. Oh, bear with me 2 seconds, sorry. I wonder the virtual machines. No. Okay. That might work at the end of the talk. The joystick is literally going to give us some pitch demand. It's like working with children and animals, isn't it? You should never do either. Okay, we're going to run out of time, but come down and see us on the stand. Maybe not at the end of today, but so this is basically running the model. You can see here, measured pitch angle, and the controller output on the right there. You can see it's complex control system, but that's what you can do in a very short amount of time. So let me shut this off for a minute. just come back to the slide because I know we're running short on time. So. So let's rush these a little bit. Models, you've kind of seen them. So if we've got time here, I'd love to show you the test sequencing that you can do, the stimulus profile generation. As I said, it's just so it's just applying ramps and applying different stimuli to the system. I'm not going to create one now; it's going to take too long. I'd also got a few. I apologise, just running out of time here. I've got a few things set up. So you can run TestStand and you can run these models. You can start the model. You can stop the model. You can apply stimulus through TestStand steps. There's already pre-prepared steps that you can. I don't know if you can see them in here, but initializing VeriStand and data logging, get channel set value, get channel and set channel value, and TestStand integration. Other automation, so that because you've got this .NET API that you can run with the system, that you can just run a Python script. And if anybody's interested, come and have a look afterwards because we've got a Python script where you can run a stimulus profile on here. So automating through TestStand or any other method to run and stimulate your real-time test.
David, could you clarify? So if you've got a full validation test program,
Yep.
Where you've got a bunch of tests that are defined in requirement, you can automate those, put those into TestStand, and then use TestStand to call VeriStand for their choices.
Exactly, yeah, kind of use it as a hierarchy. So using TestStand as a sequence engine, if you like, and then using this to do the real-time simulation and test. So just to kind of cover off what we were talking about earlier, the test flow cell, I'm just going to rattle through these. So the Rio, a PXI system with a MIXI Rio has got 14 C-series slots on it. For this first test cell system, we had a PXI with 3 14-slot chassis underneath. No problem for VeriStand. Immediately recognises everything, and we could provide over 500 channels of data and log that data at a good kilohertz rate we were running that loop at. So again, these are all the requirements for that first test system. PID models running. Okay, these ones running at 100 hertz. They wanted to use their own PID models, so we could swap those in. We could use the LabVIEW models and swap in other LabVIEW models, the Simulink models. Alarming comes off the shelf with VeriStand. Sequencing off the shelf. Video capture, well, that's kind of a little. We could add that as custom devices. That's not an easy thing to do, but definitely possible with the tools that are available. A high-speed dynamometer. Again, you'll see all of these are green because all of the functions we found that we could do via the APIs. Embedded software validation, different system definitions. In fact, using the API again, we could take a customer's Excel spreadsheet and create a system definition from there. You know, they kept control of their Excel spreadsheet. We could automate the system definition, inputs, mapping model to outputs. Alarming built in, multiple models. You can run infinite amount of models if you don't take very long at all. You can run huge amounts of parallel models. A channel monitoring and alarming is again built in. Again, you'll see these are all ticked off by the framework with work on our side, but not too much work. So I'm kind of getting to the end here, but I just wanted, apologies for the formatting on here, I just wanted to kind of give you a little bit of an insight on why we've chosen to use VeriStand and how it's kind of helped us as an integrator. It's allowed us to build on top of an infrastructure which is good and works. It's interoperable with many other languages off the shelf. And what we found is that taking that to customers, we can immediately get them something up and running within a couple of days, maybe even a week. They can see results, they can put their models in, and when we leave, they don't just have a fixed configuration that they can use, they have a system that they can take on. They can, even their operators, without delving into LabVIEW if they don't need to, can change and combine new models. Their designers can use their MATLAB Simulink models and update them. And as you see the trends that we've seen in test cells, increasing complexity, test case coverage, automating these tests is really important as well. So you can do that. You can do that a number of ways through TestStand, through Python, through any kind of scripting framework. But what we've found through our experience is great quality, less time, lower risk for the customer, giving them flexibility, using and focusing on their requirements rather than building that core framework. So sorry to rush the end bit there. I apologise for not getting to everything, but thank you for coming. If you happen to be in Birmingham over the next couple of days, we're taking this demo and we can go into more detail about the demo and how we kind of integrate Hill systems and test cells. At the Advanced Engineering Show the next couple of days, we're actually piggybacking on the NI stand, so we'll be in a corner of the NI stand. So thank you for your time. I hope it was useful kind of learning what we kind of have learned through using VeriStand. And if you do use it, have fun. It's a good framework. And thank you again. And in the meantime, I'll try and get this up and running if anybody wants to see it.